record. Right, we're good to go. Vishal, thanks for picking this up today. Vishal's covering for me because I've not really made an awful lot of progress on AI Materialist, although I did do some today. I've ran over the last 24 hours, I've ran another probably 12 epochs through the full data set, and I've generated the masks that we need for processing the full data set. So it's burnt about 24 hours of full K80 GPU. I didn't go for the expensive one because they weren't available. But yeah, so anyway, I'm running low on Google Cloud Platform credits now. But I figure probably what I'll do is I'll take that and share the masks with everyone so they don't have to generate them, because it took about, I would have said, about 5 or 6 hours to generate all the masks. And it's CPU bound, so but I don't think there's any way I could really have sped it up. So I just I loaded it onto a smaller instance and ran it that way. Okay, so Vishal's going to take us through EfficientNet. I had a quick look at the paper earlier. It's quite interesting stuff. Vishal, are you going to give us an overview of how EfficientNet works as well as the code?
Yeah, I'll go through a bit, not like in depth, because yeah, there's still some things in that that I don't understand really well. But yeah, just general idea of it. So yeah,
right.
So my introduction was to fast AI. So I started in doing this Food 101 thing just when we started doing food thingy. But I was like, I'll stick to this thing for longer. And as Jeremy says, like, do one problem, like finish one problem properly. So like I'll try to beat, if I can beat the current state of an art. So that's what I was trying from whenever like we tried doing food. I think it's been like 5 weeks or 6 weeks, something like that. So I started with simple Inception V3 in Keras, but that wasn't going anywhere for me because but there was a lot of learning in that too, but I was not able to get to the accuracy which I was trying to get to. But then in fast AI, directly jumping into the best, which are now like EfficientNet, which we can see in paper with code. So you might be aware about this website where they publish all the latest papers and state-of-an-art results. So you can go for like image classification and different type of medical data set, methodological graphs, all kind of different things, and what are the best results right now. So there is one for Food 101 as well. Oh, no, sorry, not this one. Oops. It comes under fine grain problems, Food 101. Yep, here it is. So there are some data sets which comes under fine grained image classification. Food 101 is one of those. There are like cars data set, flights data set, and some other data sets which they are called fine grained because there's not much difference between classes. A lot of food items look very similar. And similarly with cars and aeroplanes. So it's not like diverse data sets. So they have like a separate category for this. So right now the best results, which I saw like for EfficientNet B7, and this is the paper from where I got to know about the paper. But more importantly, as Jeremy also says in like most of his videos on fast AI, that most of the things that these super high and this latest research paper do, we can do it with ResNet as well. ResNet is like really good when it comes to image classification. So instead of like directly jumping into EfficientNet, I tried doing something with ResNet as well. And to be honest, with ResNet 152, I was able to get accuracy of 91%, which is like pretty close to it. But if we go to the paper and see what they are claiming about when they tried ResNet 152, what results they got. For Food 101, here it is. So these are like different fine-grained data sets, like bird snaps, Stanford cars, flowers. So here's the food. And if you see in the food, ResNet 152 is the star. And they are claiming like with ResNet 152, they were able to get only 87% accuracy, this team. But I was able to get somewhere here, even better than all these. Not as good as G pipes, but G pipes are like, they take crazy amount of parameters. Like G pipes, which are the best before EfficientNet B7 came for Food 101. They took 556 million parameters, which is a lot. You need some good infrastructure to run G pipes. And then that's what EfficientNet is trying to do here. So what I'll do today is I'll go through my ResNet part as well, a bit of things that I did, which helped me to get to the 91% on ResNet, and EfficientNet code, the whole EfficientNet code, which allowed me to jump over these best results. So I trained it on B4, EfficientNet B4, and they got 91.5. And I was able to get like 91.8% on EfficientNet B4. And EfficientNet B7, it's still running, but it looks promising, and I think I'll be able to beat 93% as well. But it is taking a lot of time. Like each epoch takes 3.5 hours. So I'll go through the code. Like we can do a bit of coding, and instead of going, okay, I'll not go to the ResNet one. I'll just start doing the code here, which I use for EfficientNet, and the things which I use in the ResNet thing were also in EfficientNet. Some tweaks which I'll mention. Like what are those? So starting with simple checking our processes and my GPU. So we need some good GPUs if we are running EfficientNet. So EfficientNet from B0 to B, it's like, sorry, EfficientNet had different categories. So it has like, it goes from B0 to B7. So what are these? To understand those, we have to go and see the paper again. So what EfficientNet tells is that that usually what we do is like to improve the accuracy, either we increase the resolution of the images or we go deeper in the network. So, but there is no standard way of telling like how much deep you should go, what resolution you should use. And there is one more thing called widening the network, which was a paper came in 2017, which claimed that instead of going deeper and deeper into the network, you can actually widen the network, which means like you can increase the number of feature maps. So this what it does, it gives you same kind of accuracy as like deeper networks, but with very shallow number of layers, like maybe 16 or 17 layers, which performs equal to ResNet 50. But the number of features which you use, feature maps you use, like they increase 4 times. So what EfficientNet tells that we take all these 3 things and we tell you that how you should scale these 3 things to get the best results. So they came out with a equation of how you should scale your model in terms of both depth, width, and resolution. So that's what they are talking about here. Let me see where it is. Yep, these parameters. And so when I started doing it with the basic form of EfficientNet, which is like 224 is pixel, and also ResNet underneath the EfficientNet, they take MobileNet or ResNet architecture and then use these techniques of increasing the depth, width, and resolution upon the already present underlying architectures like MobileNet and ResNets. So they take either MobileNet and ResNets, and they just modify them so that how depth, width, and resolution should be increased, and that's how we get EfficientNet. And they give a good comparison as well, but
so is it almost like automating the approach Jeremy was showing us, where we trained on a smaller network?
Yes, yes. So that's what it does. So we usually, like on a smaller images, the network generalizes really well. And so what we do is we usually, when we train our ResNets, we train it on, let's say 24 by 224 pixels images, and we get like really good results. And then we move on to 512 by 512 results, pixel images, and we can improve the performance from there on. And also we go deeper, like first we use ResNet 50 and try to go ResNet 100 and ResNet 150 to see how the performance is increasing, and performance actually increases. But here they're saying like it's the same thing, but we do it for you. And there's like a certain value according to which you should scale these things. So like when I first read it, so I couldn't understand like what's these exact values, how you should scale those. So there's actually someone on Fast AI forum. If I can write it, Fast AI. On forum, someone actually mentioned how you should choose your parameters. So here, someone actually gave this example. It says like when you're using EfficientNet B0, the scale. So one is just telling like this is your base network, and you're using 224 by 224 images, and 0.2%, like 20% is the dropout rate within the network. But if you go from B0 to B4, so the width of your network increases by 1.4 times, depth increases by 1.8 times, your resolution should go from 224 to 380, and your dropout should go from 0.2 to 0.4. So that was really helpful for me. So I did go through, like I tried values according to these, but as this guy also says at the bottom, but in my experience, going with the B0 with higher resolution also helps as in ResNet. So we are using a smaller network, but we are increasing the resolution. So instead of using 224, I use B0, but I use 512. And there was like a drastic change in performance again. So the uh, network trained really fast because it was very small network, but because the resolutions were high, still we got like the accuracy jump from 82 to 88 or 89, something like that. So that was like good jump and quite surprising. But one thing that surprised me was when I was doing the same thing on ResNet. As I said, I took ResNet 152 and I trained it on 224 by 224 images. I got like, let's say 86% accuracy. And then I transfer the learning from 224 to 512 by 512. So the accuracy increased. But in the case of EfficientNet, I took B0 and I trained it on 224 by 224 and then tried to transfer the learning to another B0 with image resolution of 512 by 512, but there wasn't any significant change. So that was like one of the surprising thing for me. But also I need to dig a bit more into the code which was written, because EfficientNet doesn't officially come with the FastAI library yet. It's a third-party implementation. Someone wrote it, but we can use it quite fine with FastAI. And the third party is, I think I have the link. So that's the Git repo for EfficientNet code. And it's basically pretty simple. You just pip install EfficientNet PyTorch and you just do import EfficientNet and you tell like, so you tell whether you want the pre-trained B0 or like B0, B1, B3, which we saw here, which EfficientNet version you want, and do you want pre-trained or not. So pre-trained is they train it on I think Cypher 100 or ImageNet competition dataset, and So we get the pre-trained EfficientNet network from there. So I think that's pretty much the idea of efficient is you can go from B0 to B7, and with every time you increase, go from B0 to like to the next stage of EfficientNet, the depth, width, and resolution increases, and so does the performance. But it's still, because we are widening and increasing the resolution, so it creates a perfect balance of all these things, and because of this we get like state-of-an-art results with like way significantly lower number of parameters. So you see gpipe 557 million parameters was used. EfficientNet B7 just takes 66 million parameters, which is like 8.4 times smaller than the uh, gpipes, which is very significant, very significant when it comes to training. And you'll see how fast EfficientNet converges as well when I do the coding now. It converges really fast. Like it took me 47 epochs on ResNet 152 to get results like 91%. But with EfficientNet B4, which I ran, where I got like 91.8, it converts in 11 epochs. So it's like there's a drastic difference. So I think we can go back to the code now, unless you want to ask something. All right.
No, the only question I was asked, in terms of widening the network rather than deepening it, does that help when you're doing inference? I'm thinking you would obviously be able to do more of the computation in parallel, and rather than if you've got, say, 3 times as deep a network, you're when you pass from one layer to the next, you obviously have to complete the previous one before you move on. That makes sense.
Sorry, you're talking about inferences.
Yeah, the inference speed for wider rather than deeper. I think you get a slightly higher performance from doing that.
Yes, we get like quite a significant performance change. The reason is when we widen the network, so the resource which we need more is memory, not the processing. We need more memory to get more feature maps. But when we go from one layer to another with more feature maps, the I think I might be wrong, but the GPU doesn't have to scale a lot from going from one layer to another to do all those processings. It just have to get more memory. This is the paper, and they did like some minor changes. This is a wide residual network aiming 2017, which gave the idea like we can widen the network. And they basically took the ResNet and just changed some things, but mostly the idea was you increase the number of feature maps by 4 times. That's it. They did change some of the things, like in ResNet layers were like convolution layer, then there was batch normalization, and there was ReLU. They switched like batch normalization, convolution layers, and ReLU. But apart from it, I think mostly things are same. It's just they change the number of features. I haven't read this paper. I saw a summary of this paper by a guy on YouTube. He mentioned it. So, and he said the same thing, like the performance, the only impact is on the memory. So if you have like a graphic card with higher memory bandwidth, it trains faster because it takes less epochs and the network is smaller to converge. But the processing power decreases a lot. Yep. We can. I think I can go through this paper later. I haven't read this paper though completely. Just to get an idea, I went through it. Okay. Cool. So right now, I think the latest version of fast AI has some issue with uh, Torch, PyTorch 1.5 release. So what I was, like everything works fine, but the transformation function, especially rotation, it creates some issues and the whole program just crashed. So what I was doing, like I was uh, going back to the 1.4.0 Torch and 0.5.0 Torch version, or you can download the latest dev code, like dev branch from the GitHub, and it works fine as well. But it creates some issues for me. So for now, I'm working on 1.4.0 unless the new release comes up for FastAI or Torch. Okay. Next, what I like to do is I like to keep all my things in a folder directory called models, uh, or like any directory, instead of keeping all the results in the like default place. So we should have our models here. We'll keep our results, our trained models here, and results as well. Next thing is your regular fast AI stuff. Nice. Then we need to download the data and untar it. But this Food 101 dataset is already available with fast AI. So fast AI food dataset. So we don't have to like go to the website and download from there. Should give a link. Oops. Where is it going? Basically, we don't have to go to the link and untar. We just give this command untar underscore data and URLs dot food. So URLs contain a lot of data sets. We can just check all these data sets, Canway, Card, Cypher, Cypher 100, Coco, all the popular data sets are there. Yes. So we take the food one, and this food is just Food 101 data sets. And it takes like 5 to 6 minutes. So what I did, I actually, before joining the video, I ran this. So I think it shouldn't take much time because it's already there. Yep. So basically it downloads the data sets like 5 to 6 minutes because it's 5 GB, and then it untars it. So it takes like a 10-minute job. So we can see what is there with us now. Oops. Oh, sorry. Yeah, so we have images, we have H5 file, we have some text file, JSON files. Now, I also have this data on my computer already. So basically, we get this images folder where we have all the categories of data as in like the name of the category as in folder, and each category contains 1,000 food images. And it contains some metadata, and metadata contains two JSON files and two text files which contain, out of all these data, which images are test images and which are train images. So it already comes with a distribution of test and train images. And if you see on the train images, it just basically tells like out of like apple pie, the category is apple pie, and which image is basically is train image. All right. So because it instead, like how usually fast AI likes data is like already distributed into train and test, but the whole data set here is just under one images category. So we need to do an operation so that we get a data frame where in this data frame, we get two data frames, train data frames and test data frame, which we can pass on to later to understand like which is to tell faster which is the train data set and test data set. So it's basically just going into train.txt and test.txt and creating two columns, label and name. And under label and name, it's just telling like the label is the first part of the string before the slash, which was apple pie, and name will contain the later part of the string, which was the the name of the image, which is a number. So if we run it, it should create two data frames. So let's see, train data frame dot head. Yep. So it's saying it's label, and this is the name, apple pie slash this one dot jpg. And similarly, we have data for test. So now it will be easier for us to pass to fast.ai. We just have to say like, okay, this is the test data, this is the train data. And fast.ai will automatically pick the labels from this label category. Cool. Now, what I like to do is, I got this code from somewhere in the Kaggle, and it works really well. So what we usually do is we seed so that to get the same results every time we of the randomization. But when we do this, we usually do this only for when we are creating the data and creating the split between the data, like out of the training set. For every training, how much will be for train set and how much is for validation set. But when we use this, it actually also seeds a lot of other parameters, which like for torch CUDA and backend CUDDN, just not just for NP random seed, and it actually helps to generate the same images. But still, I see you don't get like exactly the same data set results, but it's very close to that. Now, what we are going to do today is we are going to train our model on, so we are going to try training this Food 101 data sets on EfficientNet 0, which is the smallest one. And we'll do it for 224 by 224 pixel. And we'll see how fast it converges and so that we can also cover the training in this video. And later we can see I have that notebook with me where I trained it on for B4 with 512 by 502 pixel, and where we got the results better than the already available one. So let's define the batch size. So batch size 64 will work fine, and image size of 224 and 224 will work perfect. Now, usually when we do the training on image classification problems through fast.ai, and we have to do the transformation, we use get transform function, which we also used in some other this meetups we had, and where we did image classification. So we just use get transform, and it gives you default transform. But what goes underneath is we are doing basically this kind of stuff. We are just telling like what kind of transformation we want, and for each transformation, like whether it's zoom, then we tell like how much should we zoom from, like going from original size to 1.4 times. And other important thing is this p. So we are telling it's like on how much % of the data, like what's the probability that this zoom transformation should be applied. So I'm saying like to 75% of the data, it should be applied. So similarly, this is one of the most important things I think, which helped me to beat the current state of art, was these transformations. So transformations are pretty important, and I think you have to play with transformation a lot. And I'm applying a lot of transformations because this data set has it's not very clean data set. It has impurities, and even when the classes are all right and images are like okay, still there's like some images have like really bright, some images are really dark, somewhere food is inverted. It's very general data sets, like how we get in the real life, rather than like satellite images images or something where all images are kind of same. So transformation, which I applied, was most of the things were quite basic, apart from brightness, contrast, jitter. I applied skew and squish. We can go to the fast.ai website and documentation and can see what all these transformation do. But basically, it's just a minor change in colors or shape or basically, yeah, flips and rotation. And you see, it's a if you see DF transformation, it has like two elements in it. First is this, and the second is this. So the first one is for training, and second one we are saying like we don't want all these transformation for the validation set. Only train set, you apply these transformation on the training set, and for validation we don't apply any transformation, just a simple crop pad. Right. So this is our transformation, and then we can create our data. Right. So we are going to create our data from our image list, which is already a function with fast.ai library, and from there we use from_df. We are creating from data frames as we created two data frames above here, train data frame and test data frame. And so we just have to tell it which data frame are we talking about. So we are going to train on our train data frames. Perfect. And where this train and where are the images? So we get path to the images. Path should be path equals to this. And oops. Yep. So we're saying like path equals to the default path, which is this /images. And yep, and calls one, which is column one, where the images in the data frame. So column 0 contains the labels and images are in column 1. Perfect. And then we do dot split. So we are telling like how much on every training data should go in training set and how much should go in validation set. So trained by a random person. 0.2. And we have to tell like, so we told them where the images are, but we haven't told the, should be all right. Yeah, we haven't told the data like where the labels are. So we do label underscore from data frame as well. But instead of column 1, my labels were in column 0. So call equals to 0. And then what kind of transformations we want? Transform. So the transformation which we want is this. And what kind of size of the images we need? So size we already defined, which was 224. So all the images should be changed to size of 224 and transform to this kind of transformation, which I just mentioned. Perfect. And then we have to define we create a data bunch out of it. And we define the batch size. We have also declared the batch size above, which is 64. So we're just giving 64 value here. And finally, normalize. So what kind of normalization we want for normalized American? Yeah. So we want ImageNet stats, the default one, which comes with the ImageNet normalization, but we can change to different normalization if you want. for now, we'll use the ImageNet normalization. Perfect. Should not get any error. There's an error. Oh, not yes, it should be data frame. Perfect. Now comes the EfficientNet thing. So we have downloaded the data. Sorry, we have told the transformation and told like created a data bunch. Now, as I told you, this EfficientNet code is a third-party implementation. Someone wrote it for PyTorch because the original paper, although it's like paper with code, they gave the code in the research paper. They gave the source code, but they implemented it in Keras originally. If you go on the Git repo, you can actually see, and they run it on TPU. So what we are going to do, so some guy actually implemented it in PyTorch. So here's the PyTorch implementation. And as I told you earlier, it's quite simple to import the libraries. We are going to install. So pip install. Let's do upgrade. If I already have, I ran this before in the same runtime. So PyTorch. Perfect. And we should be able to install EfficientNet PyTorch using it. Yep. So we have EfficientNet with us now, library. So we import the class from EfficientNet PyTorch, import EfficientNet. Perfect. Now, as I told you earlier, we can get the pre-trained one or non-trained one version of the EfficientNet, and what kind of efficient net we want. We also tell here. So into our variable called model, we go like EfficientNet.from pre-trained and EfficientNet v4. So we'll do v0 so that we can see the functioning of this here. EfficientNet v0, yeah, I think should be all right. And yep, it's being downloaded, and as you can see, the original pre-trained EfficientNet is very small. It's like 20 MB. Perfect. So loaded pre-trained weights for EfficientNet v0. Now, it's just basically we are using the learner class. It's quite simple now from here on. So we are just telling we want accuracy and top 5 accuracy. We're interested in both. So we use both metrics. Data we already defined here. We created the data bunch. Model is, we just downloaded the EfficientNet pre-trained model, which is v0. And we want the callback function to show us graph once every time it gets trained. So we see the graph with validation loss, accuracy, and training loss. And we are using mixed precision. It's one of those important things, I think, which helps a lot, mixed precision, because what it basically does is, like, by default floating point, it takes 32 bytes. Sorry. I forgot. By default, it takes 32, whatever. and we fast.ai gives us provision. It's one of those libraries which gives you provision when you can train it on 16 bits instead of 32 bits. So what it does, like, everything on a graphic card just takes half the size, and it helps you to train the model faster and with less RAM. And I haven't worked with it a lot to see whether there's an impact on accuracy as well. But I have seen some blogs where people have mentioning, like, when they train it with mixed precision, with a smaller floating point precision instead of 32 bit, 16 bit, they get a slight accuracy improvement as well. I need to check that. I need to read about this a little bit more. But I think it's one of those things. It's like pretty neat tricks to train your model. So, and also when we use CNN Learner, which we use for ResNet, the thing is it by default breaks the network into three parts. So when we train our network, it trains different part of the networks with different learning rates. Therefore, we give a slice when we do learn fit one cycle. So we give a slice. So we say like the later part of the network, which are the extra layers which we have added just for our model. The initial is just trained on the ImageNet computation. We don't want to change the initial layers a lot. We just want to make changes in the later layers. So we give higher learning rate to the later layers and lower learning rate to the previous layers. But because it's a third-party implementation and we are using learner class, so it by default doesn't break our EfficientNet model into the same way as it does for the ResNet. So we explicitly have to tell it that uh, split our model, and I just got it from internet. I don't know exactly how it's splitting the model so that it performs, it trains the model exactly like how we train our ResNet, so that it breaks the ResNet into three, sorry, it breaks the model into three parts and train slowly on the earlier part of the network and faster on the later part. We don't have to do it in our CNN learner, but when we are using this learner class and we are using third party, we have to explicitly tell that you should split it the same way. Otherwise, it will work, but you will not get the same performance. Perfect. Let's go ahead. Cool. Model is loaded. Gives a good idea about the model. Now, next thing is we'll do a record plot to see what learning rate we should use. And in the last meetup, I was talking about the suggestion equals to true, right, Finlay, where I was telling like it actually gives you the point which you can use, and it's quite accurate. So let's see.
I'd be interested to see how that performs on some of the more complicated
Yeah,
graphs.
yeah, it doesn't.
Some of them, as a human, I look at them and I'm like, I don't know what.
Yeah, and it doesn't. It breaks. But like when I never use it, to be honest. I still find my own points, but it's still a good indication. Like I give you an idea. So it's giving you this big red dot, right? So it's telling you like you should use minimum like 9 e raised to the power of minus 0.3. It's saying like you should use this value. But I think I'm not going to use. It's all right. I can use that. Yeah, I'll use that. The curve is sharpest here. Instead of going, yeah, all right. I think it gives the perfect point right now. So what I'll do is I'll make the learning rate equals to 9 e raised to the power of minus 3. And we do learn dot fit one cycle with slicing as I copy paste the code so that I don't have to write much. So should we? I think we should do it only once for now to see like how it is behaving, and let's save the results in the model directory we created. Yeah, so as I was saying, like we need this split. If we don't do the learn.split, this slicing will not work. You'll get error here. It says like, how are we going to slice the network if there is no split in the network already? Cool. Okay, so our .pth file should go, and we should train our EfficientNet now. Yep. And it should train under 10 minutes. All right. It will take around 10 minutes from here. So in the meantime, I can show you the file open notebook. The one more thing. Oops, sorry. No, cancel. Color. One more thing which I did, which I skipped in this notebook, that I use in ResNet 152 that actually helped to improve the performance, and that is okay. Let's go to color into notebook. Ba ba ba. Oh, ResNet 152. Yeah. Oh, we don't have the images. So basically, what we do is Fast AI has like a thing where you can create widgets within your notebook, and you can actually interact for those widgets. And these widgets are very helpful for cleaning the images which are misclassified, or the images like similar images in the data set. So I think once it is trained, we can do it here as well, but it will take some good 8 minutes. So what basically the idea is, uh, you just use fast AI widgets. You again create a new data bunch, and this time you don't split the data set into training and validation set. You said like split none, so that takes all the data. And then we take our model again, and we use a class called data formatter, and then we say like find out the top losses after we did this one epoch of training. So it tells us like what top losses are, and then we just basically say like image cleaner, and this is the path. This is those images which are misclassified. So, and we get the images here, and it says like, oh, it's takoyaki or not, and then it says like delete underneath it. This is still like, it's the UI still has some issues, like this delete button is kind of hidden, but but it you can basically see sometimes that there's a delete here with the red button, and you can also change the class. So you think like, this is not guacamole. What I see here is misclassified, and this should be, let's say, pizza. So you should go and change the pizza. Or if you think like there's like an image of a human face and it says guacamole, so you can just basically delete it. What it does is when you just go next batch, next batch, next batch, so it gives you a batches of 6 images every time, and you go through this. It's kind of manual process, but it still helps you to remove some of those major anomalies, and which helps you to improve the accuracy of your model, and it does help a lot. Uh, Sorry, and you till the point where you see like 3 or 4 times when these new batches are coming, it doesn't hear any problem, and where this indicates that most of those batches which has issues have already been taken care of. So now you don't have to press any button. You just, what it does, like whenever you create next batch, a faster automatically writes these changes where the database dataset was changes, or the class of the data was changed, into a CSV file called clean.csv in your default path. And you just, instead of creating the data bunch from our default way of creating data bunch here, we then create our data bunch from this CSV file. That's the only change that happened. So instead of using that data, which was originally there, we use this clean data. So yeah, we are 50% there, and we can see the error rate went from 7 to 2.2%. And it's quite interesting because when I ran it for ResNet 152, although it's a deeper model, but still the convergence was not that quick. So training loss was 2.18, and after the whole training session. And here, even like 50%, we are already lower than 2. So it converges really, really fast. That's one of those quality of EfficientNet. Yep, I guess we have to wait 3 minutes unless uh, you have something to ask for or.
No, sorry, we'll just edit it out in the video.
Sorry.
Fast forward it.
Yeah.
The helper functions do look really good. We'll probably worth us having a look and seeing if there's any other useful ones that they've added in. Imagine there's good documentation.
What do you mean, like the models?
Yeah, well, no, the helper widgets.
Yeah.
Because I know they've got the image downloader as well.
Yeah. There are some widgets, and I think he mentioned in his videos that this is one of those areas of notebooks which people hasn't played around with a lot, because it kind of diverges from the main idea. Like people usually use notebooks just to give command and get the results. They're not using it more interactively. So he said, like, yeah, it has a lot of potential if it is used properly. We can create a lot of widgets, and a lot of widgets can come up. And like I find this is pretty easy to clean the data than other ways of cleaning the data. It is just quite impressive. After this training, we can actually try the cleaning with a widget, like some batches.
I suppose one of the things though you won't want to do is remove the grainier, less good images. You probably want to keep those slightly more difficult to classify ones in there. You don't want to make it too easier for your model.
Yeah. But because this dataset has so many problems already, so you'll be surprised to see like what kind of images are categorized as food here. Like there's a teddy bear and it says like it's chicken wing. Like there's like a father and son image and it says a steak, which is it can be, but yeah.
It's not what a human would have said.
Yeah. All right, so training is over. It should validate quickly. Less than a minute, 2 minutes. Running on the validation set. I guess I can increase the number of the batch size. So what usually Colab does is when I do manage, it's not happening today. When I do manage session, it just tells me how much of the GPU is being, oh, sorry, I can do this with command as well, but usually shows here how much of the memory of the GPU is being used. So if it's like something like 8 or 9 GB and I have like 16 GB, I can increase the batch size. Otherwise, I can run this command again and see how much of the GPU is used here. Initially, it was just 10 MB, but well, it's better to use. I think we can refresh the page and see here. Maybe it's not coming now. So the training happens faster if we increase the batch size. But again, I was reading a blog yesterday, that after 1 point, if you increase the batch size, your accuracy, it impacts your accuracy. So 64 is actually a really good number, like below 64. The smaller you go on your accuracy, sorry, batch size, it improves your accuracy. Otherwise, it actually impacts your accuracy if you go like batch size of 200, 250, 300. Or you might have.
Does it not update the gradient after each of the batches?
It does, but somehow there was some issue. Actually, I have that. I think I still have that blog.
Yeah, well, it's just if you think of it, if you say you've got 10,000 images and you make each batch 1,000, then you're only going to be updating your weights 10 times.
Yeah, true. But like there's a big difference between 1,000 and 64, right? So that guy took only 64 to 200. It's like 3 times. But he saw a big change in the accuracy. But going with the same thing, I think then using the batch sizes of 8 or 6 should give us better results than 64. But I don't think that works like that. Perfect. So we have training done, and we see just after one epoch of training, we are getting 72.8% accuracy on the validation side, and top 5 accuracy of 91.0%. And it's just one epoch. And on the ResNet 152, I think after first we were like 84 on this and 59 on this. So it converges really quickly. Even like that's one of those benefits of EfficientNet. It's really fast, and there are versions of it like there. Oops, I don't know why it's not working. Yep. So that's the blog from the guy, and he gave some graphs where he's telling like how batch sizes 64 to 56 and 1024 performs differently. I think after 64 it converges and there's not a big change when we go from 64 to 32 or 60. But yeah, I think it's a really long blog. It will take some time. Yeah. So training accuracy 1024, 256, 64, they're pretty close. So I think going 32 or 16 will be kind of same. But
it's interesting that they were converging on different points as well.
Yeah. Even I was surprised. I haven't read this book because it's like a book. This guy wrote a lot. But the graphs, they had some interesting results. Because I was wondering, like, so what he did, like, he took the batch size more, like bigger batch size, but then he increased the learning rate, and he found out that actually this moved closer. So if you're using bigger batch size, then use higher learning rate, and things will start to get better. And I have no clue how it works and why it should work, but it works.
I suppose that makes sense. If you're making less updates to your parameters, then you need to make the updates a little bit bigger.
Sorry, again?
I was just saying that if you're making fewer updates to your parameters, then it would make sense that to achieve the same or similar result, you need to make bigger updates at each step.
No, why will you say that? Because like if you're taking bigger changes, like we're taking bigger steps.
Well, if you say, for instance, you've got 10 times as many updates because you've got a 10 times smaller batch size, you're going to make 10 times as many movements on and adjustments to your weights. So if
true, yeah, got it.
If you use the same learning rate, even if it's all the shifts in the weights are moving in the same direction, you're going to get much more reduced change.
Yep, makes sense. Yep, got it. I actually was thinking through some other way. For example, like if you're jumping like only 10 times, then we need those 10 times to be big steps. Correct. You want me to run the widget? You want to try the widget?
Yeah, let's do that.
Otherwise, yeah. So what I'll do, I'll keep this paper here. Right. So fast AI widgets, import stuff. And as I said, like we don't want the split this time. So we create a new data set and we say to it like, all right, labels here. So we're doing split none and everything is kind of same apart from normalization. So we're not also normalizing. We create the new data set. Perfect. And then we use the same learner. But on the new data, so the data value is updated, everything else will remain same. So the data bunch is changed. Yep, no issues with that. And now we use and now we have already trained it on one epoch. So we use this to load the learner. So whatever we have learned, we'll load that back into our model. To see, we have to see the top losses on whatever we have learned already. So I usually like to do like 3 epochs and then see top losses on after 3 epochs, but it works fine with even 1 epoch. So it will get an idea which some images which will be totally off and which will have like a loss value of really high. So we'll do .log and we'll just copy path and paste in here. Oh, sorry, we don't give .pth. All right, so we have loaded this epoch which we learned, the model, and then finally we just use top data formatter.top classes on it. Top losses, sorry, not top classes. Will be it. And we just replace the learn here. Perfect. I guess it will take some time. It's going to take around 7 minutes to go through all the data again. So I think it's kind of like another epoch. It's going through all the data, but without normalization and split, and checking out what were the top losses with this trained model. So, okay, we can come to it again. And meanwhile, you can see if I did some other changes to my notebook as well or not, so that I'm not missing on anything. EfficientNet B4. Yep, it's kind of same. So after 3 epochs on B4, we were talking about 84% accuracy, 96. Here, then I clean the data, and then, yeah, one more thing that I found, it's one of those things which if someone want to write a research paper, is I found Dropout really interesting. Like when I was doing ResNet, let me bring that back. So usually what I find, like the way I train my models, like they go fine. My validation accuracy is valid loss is lower than my training loss, then it will become same. Then I started training on 5 by 12, 512 by 512, but it doesn't converge. Like if my training loss is over my validation loss, it means I'm underfitting my model. And like there are so many things already, like dropouts and things which help us to create the balance between like to not go overfit our model. But for underfit, I always get the issues. So I always end up underfitting the model. I don't know why. So this shouldn't be up than this at the end. This should be below it always. So I've tried like a lot of epochs as well, and also I played around with dropouts a bit. So either you take uh, lot of epochs and let it converge, but after one point I found out like it doesn't converge at all. It just stays same, and uh, but we can do two things. Either we can change weight decay or we can change dropouts. Both of these do help a bit, but for EfficientNet, like when we do dropout, so you see I'm changing the value of dropout here. So I'm changing PS 0.2. So I'm changing when CNN Learner, it's for ResNet 152, which I use. So when I use that, I'm telling like only do dropout on 20% of the values. And also dropout works very like for the model, for the layers, or which came or pre-trained, uh, I think the dropout is 0.25, and the dropout on the layers which were created for just for our problem is 0.5%. And so we can change this dropout value and it does go down. But I found a pattern like when we increase or decrease the dropout, just how we change the learning rate, there is a change in performance. So I think it's something if someone wants to like try and see whether this theory works or not. So change dropout just like learning it slowly with or every time you train with new epoch, and I think it does improve the performance. So for now, fast.ai just do two values like 0.5, 0.25. So it's one of those things if you want to try and want to write a paper. Maybe it will work. Maybe result will work. So it's just one of my theories. So I might give it a go after my EfficientNet thing is over. But I can only do it with the CNN learner class. By default, the learner class in fast.ai doesn't give this. So there's nothing like PS here. So because it's third party, so I think I have to write by myself some add-ons into the code to see whether I can do the dropout so that my model doesn't underfit first of all, and and just try these values so that it goes down with each epoch, uh, and I can see the results whether what I'm thinking works or not.
Mm-hmm. Well, that's the conclusion we all came to when we looked into it last time, is that it does seem to be the combination of the efforts built into it to stop us overfitting was what was causing us to achieve worse training results than we were getting in validation, because you were removing all the dropout and you were allowing it to work using a static network.
Mm-hmm. Yeah, but again, what I'm saying is like instead of dropout being just two static values, which Jeremy says like he has done a lot of experiments and the best value he found was 0.25% for ResNet and 0.5 for the later layers. But I think instead of being like one static values, they can around with and find out like whether we see a performance jump or not. And I think there could be a performance change if we play around with these values. Instead of being static values, they change with the epoch. Just we slice the network and do learning rate. Like we use different learning rates with each epoch. Yeah, that'll be interesting to see. Like after some time and see, I'll tell you whether it worked or not after this EfficientNet thing. Okay, so it should be perfect. Now Okay, we have that. I think we just have to do just one command, which is image cleaner, sorry. Uh, should get those stop losses. Perfect. So does this look like a garlic bread? Uh, can be. These are not scallops, for sure. Deviled egg, true.
Well, it's a scallop, but it's been baked with cheese on it.
Okay.
It is in the shell.
I think everything is all right. We can't even these are escargots, but we can't see them. Those snails will be inside.
The deviled eggs
Uh,
are being a bit cartoonish.
yeah. Next veg. Sushi, dumpling. This is not chicken wings.
No.
This is hot dog. If it is something is closest to it, so we can do hot dog. Lasagna. This is not strawberry shortcake. This is some weird stuff. But even then, like we these are still close, but there are like some images in this dataset. I think because we just trained, that's why I like to do it like for 3 epochs, and then the training losses are a little more obvious. Still, it's not there, but should see those very weird results. This is not cheesecake. This is ice cream. This is not onion ring. This is some chips. Like this is totally weird. This is not fish and chips. This is not taco. Yeah, so it helps to clean those things. This is not mac and cheese. This is not pizza. Yeah. All right.
That's interesting. Oh, thanks for showing us that. I'm definitely going to start
Sorry?
using. Thanks for showing us that. I'm definitely going to start using some of these.
It does actually. I think I got um, I did some manual work to be honest when I was trying. So I went 200 batches. It took me half an hour. So like this is one batch. We go to another batch. This is like second. So I did like 200 times. And I think I got 1% accuracy change just by doing all that. Yeah. So let's see. So let's say like we made some changes. Uh, and then we should be able to create a data bunch from the clean ravioli. These are not pancakes, these are waffles. This is garlic bread, nachos. These are oysters. Cool. And now we should be able to. So if we see path dot ls, we have clean.csv now here. Is added, and it just have those changes which we just made. So instead of creating data bunch from data frames, what we'll do is create the data bunch, but from CSV. I give the path for we say like valid percentage is 20%, and we give clean.csv instead of giving the data frame we're using. Rest everything remains same. Like transformations which we defined earlier will remain same, and normalization. And also there's a thing here with image data bunch from CSV that we can add. It's called number of workers. So if you see the first command, cores I have, CPU cores 2. I think by default it doesn't use all the cores to create data bunch, but I can tell it like, okay, use both of my cores to create data bunch. So you check how many cores, just give 4, so it will happen quickly. If you have like a lot of data and it takes time to create it, although it doesn't take much time to create data bunch stuff. So it's not a major time saver. Yep, I think uh, that's doesn't look good. What happened? Okay. So it's not clean. Dot, oh, path is not right. Perfect. So we have the data. So I think the rest is just same training on just finding a perfect point and optimizing it. And 10 to 11 epochs, it converges really well. So if I can show you my EfficientNet 101, yeah. So I'm able to get 91.71% accuracy with TTS. So yeah, one more thing that, so without TTA, I was getting 9.22, 98.63, and with TTA, 91.7. So what is TTA? Do is when we make predictions, either we can make prediction on the directly the test images straight up, or uh, there are some techniques through which while making prediction, you can increase the accuracy. One of those technique is called tan crop. What we do in tan crop is we give the test image and we make 10 crops out of it at different regions, and we we make the probability estimate on all those regions, and we take the best values, like which value was mostly there. Again, np dot argument max. Or what we can do is something called TTA, which is inbuilt in uh, fast.ai. So what I'm doing is I'm taking the whole data set again, loading my model, and uh, I'm just saying that instead of making prediction straight up, first you do TTA. So TTA is doing those transformation on the test set again, which I did for training. So it creates several copy of the image which we want to predict value on. And on those several copies, so let's say I did all those transformations, all these transformations. So if I give an image of pad thai, so it will do all these transformation on pad thai. So it will create several copies and will make prediction on all these copies, and will then decides based upon the results which it gets, like what was the maximum value which it got. And based upon that, we actually get a performance increase again. So I was able to get 91.71, and it is just on B4. I am running B7 right now, but it is a heavy job, and I think fast.ai doesn't support multi GPU still yet, multiple GPU support, so I can't run it on AWS or somewhere where they have two P3s or two V100, sorry, two P100s or two V100s or three V100s combined together, so that I can run it in a shorter period of time. But it will take me, I think, several days of training. Fast.ai, I read somewhere, I might be wrong, that fast.ai does support multiple GPUs, but I think fast.ai doesn't support what I read, multiple GPU training yet. Yep, and yeah, it's still being trained right now. And the clean data which I created using B4, I'm using in the B7. I'm not cleaning it again. So it just saves me a lot of time. And still there. So I think that's pretty much it, what I wanted to cover. Next thing from here that which I think can improve performance on this is dropout, because there was no dropout. So I want to, because my model is state under fitting. So I think, if I can get this closer by changing the dropout value, how I did for ResNet. So for that, I think I need to implement if someone wants to implement something in the main third-party implementation of EfficientNet, which is uh, or use the other version of EfficientNet which are available now. So there are newer version of EfficientNet are now available. They are called fix EfficientNet, small minute changes, and I think the current state of an art for ImageNet competition is fix EfficientNet. Paper with code. Let's go there, and we just quickly see whether what was the current best classifier for image classification. I think it's EfficientNet, where with some fix to it. Yeah, fix EfficientNet L2. So this is the paper. Where so the current leader on ImageNet dataset is EfficientNet. Yeah. But the B4 and B7 are like, B7 is on 23rd now. So there's like lot of like this B7 to 26, lot of changes to EfficientNet has already been made. Oops, sorry, we were looking, my net is slow. B6, B5, EfficientNet B5 is on 40th. So I ran on B4. So I think if I run just simply B4, I should be top 50. I think B4 was 51st on ImageNet competition. But now, same EfficientNet, people have made a lot of changes to it, like some tweaks to it. And this one is the best one. And I think it came last month. I think that's it, unless you have some more questions.
Oh, that was really great, Vishal. I guess the only thing to say is, are you able to share your notebooks on the Slack channel?
Yeah, I'll share. I'm still running, and I don't know whether how long will it take. It'll take 2-3 days of training, because I just do like 3 epochs, and it takes 11 hours. But a good thing for me is like it just takes 16. It will take around 15 to 16. I'll share my B4 one. Yeah, and I'm also thinking of writing a blog because go in a paper, but it can be a really good blog. So as well when I write it, like what all things I did.
Cool. All right, look forward to that. Right, should we close up the recording and we can all get our dinners?
Cool.
Okay. Thanks again, Vishal. Cheers.
That was brilliant. Thanks very much.
No worries.